Green hydrogen attracts enormous attention because it connects renewable power with industry, transport, fertilizers, shipping, and energy security. But an attractive idea is not automatically an investable project. Between concept and construction lies a difficult development journey involving customers, land, electricity, water, engineering, permits, environmental safeguards, commercial contracts, risk allocation, and financing. This video examines what global climate finance programs and public development institutions appear to support most consistently. The central lesson is simple. Financiers rarely fund an electrolyzer in isolation. They support credible systems that can convert public resources, technical preparation, and private capital into durable clean energy infrastructure. The headline question is not only who will finance construction, it is who pays for the work required before construction can begin. Developers must fund market studies, site screening, resource assessments, engineering, environmental and social work, legal structuring, financial modeling, and customer negotiations long before the project earns revenue. This early stage gap is where many hydrogen concepts stall. Capital providers want evidence before committing large sums, yet developers need money to create that evidence. Successful climate finance structures address this paradox by using grants, technical assistance, concessional capital, guarantees, public facilities, and sponsor contributions to move projects gradually from uncertainty toward investment readiness. Climate finance generally supports more than equipment procurement. It often finances the enabling systems surrounding the technology, policy frameworks, institutional capacity, feasibility work, environmental safeguards, market creation, infrastructure, risk mitigation, and private capital mobilization. This matters because an electrolyzer cannot create a viable project by itself. It needs dependable renewable electricity, treated water, storage, transport, permits, customers, operating capability, and a financial structure that can withstand uncertainty. The strongest programs therefore connect public policy, project preparation, commercial demand, and risk sharing. For developers, the implication is clear. Present the project as an integrated development system with measurable climate and economic outcomes, not simply as a machine purchase. Chile illustrates the financing facility model. Rather than relying on one grant to build one plant, a dedicated facility can assemble public, concessional, and private capital to support a pipeline of projects. The purpose is to reduce early risks, strengthen project preparation, and make individual investments more attractive to commercial financiers. A facility can offer different tools at different stages, including technical assistance, concessional loans, guarantees, and co-financing. This approach creates scale because it builds repeatable appraisal standards and a national project pipeline. The second Chile slide focuses on how a financing facility turns capital into a bankable pipeline. The facility becomes an organizing platform where projects can be screened, prepared, de-risked, and monitored under consistent standards. Public resources support activities the private market may initially avoid, while commercial capital enters as technical, regulatory, and customer risks become clearer. The goal is not simply to announce available funding. It is to create a disciplined process that identifies viable projects, rejects weak concepts, and directs support toward investments capable of reaching financial close. India represents a different but complementary model, policy, and market reform. Clear national targets, incentives, standards, infrastructure planning, and demand creation measures can reduce uncertainty across an entire market. Government action can help define what qualifies as green hydrogen, support domestic manufacturing, encourage industrial consumption, and improve the economics of early projects. These measures do not eliminate project-level risks, but they create stronger conditions for investment. Developers benefit when rules are visible, permitting pathways are clearer, and customers have reasons to sign contracts. The key lesson is that finance follows credible market signals. Every strong hydrogen project begins with a real problem, not with a preferred electrolyzer. The developer must identify the industrial, energy, transport, fertilizer, shipping, or resilience challenge that hydrogen is expected to solve. Then the project must demonstrate why hydrogen is more suitable than direct electrification, efficiency improvements, batteries, conventional fuels with mitigation, or another alternative. This discipline prevents technology-first development and unrealistic capacity assumptions. A project becomes financeable when a proposed solution creates measurable value for a customer or public objective. Hydrogen production depends on physical fundamentals that must be secured early. The project needs reliable and affordable electricity, an acceptable water source, a technically suitable site, and legally defensible land or site rights. These elements determine production cost, operating profile, permitting complexity, community impact, and expansion potential. Resource claims must be supported by data, not assumptions. Developers should evaluate grid access, renewable generation profiles, water treatment requirements, logistics, environmental constraints, and competing land uses. Financiers will examine whether the project controls the resources it depends on. This slide reinforces the same message because resource certainty deserves separate attention. It is not enough to show that a region has sunshine, wind, coastline, or available land. The project must establish how those resources will be contracted, permitted, delivered, and managed over the financing period. Electricity arrangements need credible pricing and reliability. Water supply must account for treatment, discharge, competing users, and climate stress. Site rights must cover construction, operations, pipelines, roads, storage, and future expansion. By converting regional potential into project-specific evidence, the developer reduces uncertainty. Once the problem and resources are defined, the developer should design the full system before choosing the final equipment package. The system includes renewable supply, grid interface, water treatment, electrolysis compression, storage conversion, distribution, offtake controls, safety systems, heat management, and operating strategy. Each component affects the others. Oversizing one element can increase costs without improving delivered value, while ignoring storage or customer demand profiles can make the plant difficult to operate. Technology selection should therefore follow system optimization. The best electrolyzer is not necessarily the most efficient unit on paper. It is the option that fits the project's power profile, product specification, operating conditions, maintenance capability, and commercial requirements. Feasibility is not one report completed in a single step. It is a staged process that increases evidence while limiting unnecessary expenditure. The enabling stage examines policy, institutions, market context, and strategic alignment. Pre-feasibility tests the project concept, site resources, customer case, technology options, and preliminary economics. Bankable feasibility deepens engineering, environmental work, cost estimates, risk analysis, and commercial arrangements to a level suitable for financing decisions. Investment preparation then converts the study into permits, contracts, financing documents, and an executable transaction. Each stage should have clear decision gates. Environmental and social safeguards are not administrative obstacles added after engineering. They are part of project design and bankability. Hydrogen projects can affect water resources, land use, biodiversity, communities, workers, emissions, and local infrastructure. Early engagement helps identify risks before the site layout and technology choices become expensive to change. Developers must understand permitting requirements, community concerns, labor and safety standards, cumulative impacts, and benefit-sharing expectations. Strong preparation can build trust, avoid delays, and improve access to climate finance. Financiers want evidence that the project can be constructed and operated responsibly. Different barriers require different forms of capital. Policy and institutional gaps may need technical assistance and readiness support. Early feasibility may require grants combined with sponsor equity. Shared infrastructure can justify public or multilateral development bank financing. Customer or offtake risk may be addressed through guarantees, credit enhancement, or contractual support. First-of-a-kind cost gaps may require concessional or blended finance. Mature construction with proven economics should increasingly rely on commercial debt and equity. The financing instrument must solve a defined risk rather than hide a weak project. The first financing model operates at market level. Government establishes rules, standards, incentives, certification systems, infrastructure priorities, and demand signals that allow projects to develop within a more predictable environment. Policy reform can reduce regulatory uncertainty and help customers understand future obligations or opportunities. Incentives can support early cost gaps, while infrastructure planning improves access to power, water, pipelines, ports, and logistics. Demand creation measures can encourage industrial users to enter long-term contracts. The objective is to move from isolated demonstrations toward a functioning market. This model is most effective when reforms are coordinated. The second model is a national financing facility that pools public, multilateral, concessional, and private capital. The facility appraises projects, supports preparation, allocates risk mitigation instruments, and develops a diversified pipeline. Instead of negotiating a completely new structure for every project, the facility can apply standardized eligibility criteria, safeguards, documentation, and monitoring. Strong projects may receive technical assistance, concessional debt guarantees, or co-financing depending on their gaps. As risks decline, commercial banks and investors can participate. This model helps governments move beyond one flagship project and support multiple uses, such as industry, mobility, ammonia, and exports. The third model uses shared infrastructure to serve several projects and customers. A hydrogen hub may combine grid connections, renewable supply, water treatment, pipelines, storage, roads, port facilities, loading terminals, and common safety or utility systems. Public or concessional investment can fund assets that are difficult for one private developer to finance alone, but valuable to many users. Sharing reduces duplication, lowers unit costs, and can attract producers, industrial customers, logistics companies, and exporters to one location. However, a hub still requires clear demand, access rules, tariffs, governance, and phased development. The fourth model begins with an anchor customer and designs production around real demand. The customer may be a refinery, fertilizer producer, steel plant, transport operator, power user, or export buyer. A credible offtake commitment provides a foundation for sizing, specifications, delivery arrangements, and revenue forecasts. The sponsor, technology, engineering, and operating partners then align the facility with the customer's requirements. This integrated structure can create bankable cash flow earlier, reduce market risk, and improve financing prospects. It is particularly valuable for first projects, where a smaller plant serving a defined customer may be more credible than a large export concept dependent on uncertain future markets. Climate financiers are not only selecting technologies, they are selecting evidence, readiness, and implementation capability. Strong projects usually demonstrate a real customer, credible sponsor, defined site, secure power and water, government alignment, completed preparation, measurable climate impact, and a realistic financing need. They also show a pathway for replication or scale. Financiers compare projects because concessional resources are limited. The project that requests the largest grant is not necessarily the most attractive. The strongest candidate often uses targeted public support to unlock significantly larger private investment. Bankability is therefore built through accumulated evidence. Weak projects commonly fail for predictable reasons. They have no committed customer, limited sponsor equity, undefined land, unverified power or water, incomplete studies, unrealistic scale, or excessive dependence on grants. Some assume an export market will appear after construction. Others choose equipment before confirming the problem, operating profile, or delivery route. These gaps produce unreliable costs, weak revenue forecasts, permitting delays, and high financing risk. Public finance cannot transform every concept into an investment. Developers must be willing to revise, phase, or stop projects that lack evidence. The H2Hub SOP organizes project development into 8 connected gates. Gate 1 confirms the development rationale. Gate 2 tests the sponsor and customer. Gate 3 secures site and resources. Gate 4 compares technical options. Gate 5 establishes commercial viability. Gate 6 completes bankability preparation. Gate 7 structures the financing architecture. Gate 8 confirms investment readiness. The pathway moves from idea to evidence, from evidence to bankability, and from bankability to investment. Each gate has required inputs, decisions, and outputs. The purpose is not to create paperwork for its own sake. Gate 1 asks whether the project should exist. The developer defines the real problem, explains why hydrogen is appropriate, compares non-hydrogen alternatives, and links the solution to climate, economic, and development outcomes. This gate should produce a clear concept note with the customer need, proposed product, scale logic, location rationale, success criteria, and strategic fit. It must avoid exaggerated claims and technology-driven assumptions. The central question is, does hydrogen solve the identified problem well enough to justify its cost and complexity? A strong development rationale gives every later study a clear purpose. Gate 2 tests whether credible organizations stand behind the project and whether real demand exists. The sponsor group should combine local ownership or implementation capacity with appropriate technology, engineering, operating, and financial expertise. Roles, contributions, decision rights, and responsibilities must be defined. On the customer side, the project needs a credible offtake pathway supported by evidence such as discussions, letters of intent, term sheets, or contracts. Customer requirements influence product purity, volume, delivery, reliability, and price. A capable consortium without a customer remains commercially weak, while a customer without a competent delivery team faces execution risk. Gates 3 through 5 convert the concept into a tested project configuration. Gate 3 validates site control, electricity, water, logistics, and infrastructure. Gate 4 compares technical pathways, including direct hydrogen use, conversion to ammonia or other products, storage options, and delivery methods. Gate 5 integrates cost, demand, offtake, pricing, financing assumptions, and expected returns. These gates must be iterative because resource constraints influence technology, and technology influences economics. The objective is not to force the original idea to work. It is to identify the configuration with the strongest resource fit, system fit, and commercial fit. Gates 6 through 8 turn preparation into a financeable transaction. Gate 6 completes due diligence across permits, environmental and social requirements, land, power, water, offtake, engineering, regulation, contracts, and financial modeling. Gate 7 builds a capital stack using the appropriate combination of sponsor equity, grants, concessional finance, guarantees, commercial debt, hedging, and strategic investment. Gate 8 confirms that approvals, agreements, financing commitments, governance, procurement plans, and execution arrangements are complete enough for financial close. The project should emerge as a de-risked asset, not merely a detailed study. The final lesson is preparation before scale. The most financeable projects do not begin with the largest capacity announcement. They begin with a clear problem, real customer, capable sponsor, controlled resources, optimized system, stage feasibility, responsible safeguards, and financing match the risk. Evidence then becomes a project dossier. The dossier becomes transaction, and the transaction becomes infrastructure. Once the first project performs, developers can expand capacity, add customers, share infrastructure, and replicate the model. Climate finance is most powerful when it helps projects cross the early evidence gap and then mobilizes commercial capital.